Hi. In this lecture, we're going to talk about a very simple class of models that helps us make sense of data, and these are known as categorical models. In a categorical model, what you do is you basically bin reality into different categories, and then you hope that these categories help you make better sense of the data, that they explain some of the variation in the data. I want to start out by just describing what a categorical model is like, and then we'll talk about how they can help us make sense of data. So let me give an example. A long time ago, over a decade ago, I was at a conference, and Amazon, which is a company that sells all sorts of stuff over the web, right, was just going public. And there was a discussion whether Amazon was a good investment or not. So one person who was a Wall Street investor said, no, I think it's a horrible investment. Because if you think of Amazon, all it is it's just a delivery company. Right? They've just got a big warehouse, you order stuff, they deliver it. The margins in that industry are really small. Right? There's sort of UPS and UPS and FedEx and DHL and all those sort of places. I just don't think there's any money in it. Now another person said, I'm going to put Amazon in a very different box. I'm going to put Amazon in this box that says information, because I think it's part of the new information economy. They're going to gather all this information about what consumers want. It's all going to be centrally held. They're going to be worth a ton of money. Now it turns out if you put Amazon in this information box, you probably would have invested in it, and you'd have made a lot of money. If you put Amazon in this delivery box, you wouldn't have invested in it, and you wouldn't have made a lot of money. So which box you use, right, how you categorize things, affects how you think about things, and again, what sort of decisions you make. So this leads to a phrase that one of my friends who's a psychologist once said, lump to live. So what my friend meant is this, is that we create these lumps, these boxes, these categories in order to make sense of the world. So when I look out there on the street and I see a vehicle, I don't say, oh, it looks like a 1997 Ford F-150 pickup truck. Right? Instead, I just say truck, or I just say car. Or if I look at a piece of furniture, I just say it's a dresser. I don't say it's an 1874 Chippendale dresser. I don't completely break it down. I just put things in categories. And these categories are shortcuts, right? They help us make sense of the world. Now let's think about why we model again, right? Remember, one of the reasons we model was to help us decide, strategize, and design, right? So one reason we lump is it just helps us make quicker, faster decisions. Or we just put things in categories and say, this is something I like, this is something I don't like, this is something that's risky, this is something that's not risky. Let me give some examples, give some fun examples. So the first one is, let's suppose you're a kid, and you've got to decide, what am I going to eat, and what am I not going to eat? Well, one sort of categorization you might use is the green categorization. So you might say, anything that's green, broccoli's green, a grasshopper's green, asparagus is green, all these things are green. Right? Everything else, bananas, those are yellow, candy bars, brown, orange, they're orange, pears can be green, but most of them are yellow, and strawberries, they're red. These other things aren't green. And so your rule could be, I'm going to eat anything that's not green, and I won't eat anything that's green. And so that rule will keep you safe from things like grasshoppers and asparagus. Right? So that's a rule you might follow. Now, it's not an optimal rule, because you might run into a green pear, and that green pear might be something you'd really like. But if you've been avoiding green things, you may decide, well, not going to risk it. So that's an example of a simple rule. Let's now show how you can use a rule like that to make sense of data. So now let's suppose I've got a bunch of data here, and these are different food items. And what you've got in this column right here are calories. So this is how many calories there are in each of these food items. So what I want to do is I want to make sense of why do some things have a lot of calories and some things not have a lot of calories. And so I've got this list of items. Well, the first thing that I need to try to make sense of is how much variation is there in this data? Well, to understand how much variation there is, first I've got to find out sort of what's the average value, and then variation tells me how far are things on average from that value. So if I add all this up, I've got 100 plus 250, that's 350, 440, 550, 900. Right? So we've got 900 divided by 5, so that means the mean here is 180. So on average, everything in this group has about 180 calories. And I want to ask, some things are higher, right? This is 350, and some things are lower. This is 90. I want some understanding of how much variation there is in that data. So one way to do that, we just subtract the mean from everything. So if I take 100 minus 180, that's going to be minus 80. 250 minus 80, that's going to be 70. 90 minus 180, that's minus 90. Right? 110 minus 180 is minus 70. And 350 minus 80 is 170. Well, if I add all these things up, I'm going to get minus 80 plus 70 minus 90 minus 170 plus 70. It's going to be 0 because it's going to be the same as the mean. So what I need is all these differences to be positive. So one thing I could do is I could just take the absolute value of all these things, right? And then I could add up the absolute value, and I could get 80 plus 70 is 150, plus 90 is 240, plus 70 is 310, plus 170 is 480. So I could say the total difference from the mean is 480. But what we do in statistics is we tend to do something different. We actually tend to take the difference and square it. And the reason we square it is really twofold. One is that, again, it makes everything positive, which is what I did before. And the other thing is it amplifies larger deviations. Because what we'd really like to do is prevent those huge deviations. So this is going to amplify large deviations. So if I look at the pair, I would have 100 minus 180, which is 80 squared, which is 6,400. So that's how much variation there would be. That's how much the difference from the pair to the mean squared. And if I did it for the cake, I'm going to get 250 minus 180, which is 70. And if I square that, right, I'm going to get 4,900. Now I could do this for everything, all of them, right? So for the pear, I get 6,400. For the cake, I get 4,900. For the apple, 81. For the banana, 49. For the pie, 28,900. So this is, again, if you get a long way from the mean and you square it, you get a huge effect. So square amplifies larger mistakes. Now if I add up all these numbers, I'm going to get 5,320. That's what we call the total variation. So if I plotted that data, this tells me sort of how much variation is there in that data. And what I'd like to do, let's keep track of the plot here, I'd like to put this data in categories that reduces that variation, that somehow explains why some things are high and some things are low. So what's the obvious categorization here? The obvious categorization here is that pears and apples and bananas are fruit, and cakes and pies, right, are desserts. So let's create a fruit category and a dessert category. So in the fruit, I've got one thing that's 90, one thing that's 100, and one thing that's 110. And in the dessert category, I've got one thing that's 250 and one thing that's 350. So let's look at them in more detail. If I've got 90, 100, and 110, the mean is going to be 100 here, right? The average of those three is 100. What's the total variation? Well, 90 minus 100 is just 10. So if I square that, I get 100. 100 minus 100, right, is 0. So if I square that, I get 0. And 110 minus 100 is also 10. So if I square that, I get 100. So the total variation here is just going to be 100 plus 100, or 200. So now what I've done is I've got a mean of 100 and a total variation of 200. And now if I go to this case, the mean is going to be 300, right, for the desserts. And what's the total variation? Well, for the cake, it's 250 minus 300, which is 50 squared, which is 2,500. And for the pie, it's 350 minus 300, which is also 50 squared, which is 2,500. So when I add those up, I get 5,000. All right, so let's clean this up a little bit. So what I did is by creating two categories, a fruit category and a dessert category, I now have a mean in the fruit category of 100 and a variation of 200, and a mean in the dessert category of 300 and a variation of 5,000. Now let's think about what I started out with, right? When I had all this stuff together, I had a mean of 180 and I had a variation of 53,200. Now look at how much my variation has gone down. It went from 53,000 to 5,000. So this is the idea. These categories substantially reduce the amount of variation I have left over. So think of the variation as what's unexplained. So initially I say, look, I can just say things on average have 180 calories, and I get 53,000 units of variation that's unexplained. Now I say, look, I'm going to create a categorical model that says there's fruit and desserts, and fruits have fewer calories than desserts. And you can say, well, look, it appears to be the case. Fruits have a mean of 100, desserts have a mean of 300, and the variation in the fruits is only 200, and the variation in the desserts is 5,000. So I've reduced variation a ton. What we want is we want a formal measure of how much we've reduced variation. That's actually fairly simple, right? So I've got a total variation of 5,300. Fruit variation is 200. Dessert variation is 5,000. So that gives me 5,200. So 53,000 to start, and I get 5,200 left. So what we want to ask is, how much did I explain? That's the question. How much of that variation did I explain? Well, I started out with 53,000, right? 200. And I now only have 5,200 left over. And so the amount I explained is just 53,000 minus 5,000, right, which is 48,000, right, over 53.2. So the percentage of the variation I explained was 48,000 divided by 53,000, which is a huge amount. Now I can write this more simply as just 1 minus the amount I did that's left over, 1 minus 5,200 over 53,000. So, right, because that's just a simple way to do it. And so I'm going to get that the amount of the variation I explained was 90%. So 90.2%. So that's how much of that variation I explained. This is equal to, again, that 48,000, right, divided by 53,200. It's the amount of variation that I explained. Now, formally, this is called the R squared. So this is the percentage of variation that I explained just by that simple categorization. So if the R squared is near 1, that means I explained almost all the variation, and so the model explains a lot, right? If the R squared is near 0, that means I didn't explain any of the variation, really, and the model doesn't explain very much at all. Now, the better the model, the more the larger R squared it'll have, but depending on, there could be so much variation in the data that even a great model only has an R squared of 5 or 10%. There also could be situations where the thing you're trying to explain is pretty understandable, and a good model has to have an R squared of 90%. So there's no fixed rule as to whether, what a good R squared is. It depends on what the data looks like. But within a class, sort of a class of models, or a particular data class, you can sort of figure out, okay, this is a good model, this is a bad model, based on experience. Let's push this a little bit further. We had, fruit and desserts, right? Those were our two categories. But if I had, a whole kitchen worth of food, it may be the case that, I'd want to have more categories. So I might create a vegetable category and a grains category, and then I could put everything in one of these 4 boxes. So one of the differences between sort of experts and non-experts is experts tend to have more boxes. They also tend to put the right things in the right boxes. So they tend to have useful boxes. So if you want to be good at sort of predicting things or understanding how the world works, what you have to have is a lot of categories, and you have to have those categories be the right categories. They've got to explain a lot of the variation. And we can measure how much of the variation it explains, your model explains, by using that R squared. One last point. Even if you explain a lot of the variation, it doesn't mean that you've got a good model. Let's go back to the schools case. So suppose I'm trying to figure out what makes a good school. What really leads to good school performance? So I try all sorts of different boxes. I look at schools that spend a lot of money versus schools that don't spend a lot of money. Schools that have small class sizes and big class sizes. Schools that are big, schools that are small, right? And nothing really seems to explain too much of the variation. And then I create a box that I call the equestrian box. And I put all the schools in here that have equestrian teams. And I find, oh my goodness, every school with an equestrian team is great. Well, the thing is, that doesn't mean that the equestrian team made the school good, right? So statisticians make a distinction between correlation, which is there a statistical relationship between having an equestrian team and being a good school, and causation. Did the equestrian team cause the school to be good? So remember when you think about putting it in this box, like this box right here has a bunch of good outcomes, and this box here has mostly bad outcomes, that doesn't necessarily mean that the thing that created this box, if it's the equestrian box, is the reason that the schools were good. It could be that there's some other reason. So why would you have an equestrian team? Well, you'd only have an equestrian team if you had a lot of money. And you probably also only have an equestrian team if you have a lot of parental involvement, things like that, right? A lot of support from the community. And you don't have an equestrian team if you have a lot of open space. So it could be that having an equestrian team is a proxy for things like money, parental involvement, open space, right? Those sorts of things that actually do make a school good. So even if your boxes work, that's no guarantee that they're actually the cause of why it works. Okay, so what have we learned? What we've learned is this. We've learned that the simplest kind of model you could have is just a category-based model, right? Where you sort of lump the world in different categories, and you place your data in different boxes depending on what type of data it is. So that could be information companies versus delivery companies. That could be fruits and desserts, right? And in doing that, what you can do is you can reduce the amount of variation you see in the data. So there's a total variation, which is sort of just like how much unexplained variation there was out there in the world. By putting it in boxes, you organize it in such a way that you reduce the variation. The amount at which you reduce the variation is what we call the R squared. That's the percent of variation explained. And the more variation you explain, the better your categorization is. Now clearly, if you create more boxes, you can explain more of the variation. So where we're going next is we're going to look at linear models, which in effect can create a different box for each value of x, our dependent variable. Okay, thanks.